Okay, hi everybody. We'll start a bit late, but I think we'll begin now. So today, today I'll stop talking. Like this will be my final talk for the few following weeks. And I'll tell near the end, I'll tell you what is ahead of us, like what's the plan for the next few talks. I also wrote it on the last email, but I'll say it again. And as we did in the last two talks, or maybe even three, we are reviewing the proof of MIP star is equal to RE. So I'll remind you what we've done last time. Oops, it's a bit slow. Maybe I'll do like that. Okay, so last time we started talking about introspection and self-testing, and I gave you an example about the CHSH game, and I'll recall what was the example and what were the conclusions. Then I will talk about answer reduction, because we said that we had like a big protocol and we try to reduce the sizes of the questions in this protocol and somehow reduce also the size of the answers in this protocol. And in this way, get a compressed protocol. Okay, so the destination was to have the compression theorem, like this is our goal. So this is the way compression is done. And at the end, I'll say just a few words about parallel repetition, because we had these claims that we don't lose the soundness constant, but if you do this introspection, question reduction and answer reduction and all these things, you lose something in the soundness part, but you can fix it using parallel repetition. But I will not say anything more than I have just said right now. So it will be a very brief part of today's talk. Okay. Okay, so what did we have last time? We said that at least if the questions in the game are lines and points in some F2 vector space, we can, if we can force the players to share exponentially many EPR pairs, and we can force them to measure their EPR pairs with either the X basis or the Z basis accordingly. Okay, if we have some control on how to force them to measure according to these two bases, we can force them to share to one of them to sample a line, the other one to sample a point, such that the point is uniformly distributed on this line in such a way that they don't know about each other's information. So the line player only knows that the point is on the line, and the point player only knows that the line goes through his point. Okay, so this is the, we said that if they can, if we can force them to share many EPR pairs, we are able to do this this answer reduction. We are able to make them sample their own questions. Okay, great. So then we started talking about the CHSH game, and this was the lion's share of the last talk. And we proved the following. Okay, so we had the CHSH. So let me just remind you that in the CHSH game, you have V. Oh, I need yeah. Why didn't it work? Just a moment, I think. I don't know why, but it's a bit stuck. I will stop sharing and do it again. Oops. Hopefully now it will be better. But in the CHSH game, we said that you win the quadruple of questions and answers is a winning condition if and only if the product, the sum of the answers is equal to the product of the questions modulo 2. Okay, so the XOR of the answers is equal to the end of the questions, right? This is just what I want. And we stated that if we first we showed that the optimal winning probability is 1/2 plus 1/2 square root of 2. And then we showed that if we have this strategy, so what is a strategy in the quantum case? It's just 8 matrices, 4 matrices for player A and 4 matrices for player B, such that each two of these matrices sum up to the identity. And also these are positive operators, okay? So the MIJs and NIJs are positive operators, and they sum up to the identity. And also they share some unit vector. And we stated that there is this result out of SVD decomposition that you can decompose psi, this unit vector, as a sum of UI tensor VI times CI. Okay, I need some coefficient here, such that all the CIs are non-negative and the UIs are an orthonormal basis of the left C to the D, and the VIs are an orthonormal basis of the right C to the D. So we have this vector and we have these matrices, and we know that they achieve the optimal winning probability. So if you play according to the to this strategy that comes out from these this choice of matrices, you actually achieve this number, this 1/2 plus 1/2 square root of 2. So we deduced the following things about these matrices. So first of all, these cannot be only positive operator valued measures, they must be projections. So all of these matrices satisfy that not only that they are self-adjoint positive non-negative operators, they also satisfy that Mij squared is equal to Mij, and also Nij squared is equal to Nij. Okay, so these are orthogonal projections. And we show that without loss of generality, they can share more bits. So the fact that the span of UI is equal to the span of VI is equal to C to the D was some kind of without loss of generality, but it was the most natural without loss of generality. We show that if they share more bits, they do nothing on these bits. So these bits are negligible, like they don't play any part in the strategy. And actually the matrices are projections even without these bits. Sometimes you need to add some bits, some qubits to assume something about these MIJs and NIJs, but here you don't need it. So we show that the span of the UI is equal to span of the VI, which is the whole space. And then we call these AI and BJ are just the MI0 minus MI1 and NJ0 minus NJ1. And we said that these are order 2 unitaries, as long as this is a projective valued measure. As long as this condition holds and Mi0 plus Mi1 is the identity, and also for the ends, you can show that these are order 2 unitaries. So this is a very general thing. But the following condition isn't very general. The fact that if you take the A1 and multiply it by A0, it's minus A0 times A1. So they anti-commute. This comes from our analysis. This was very hard to show. The fact that these are order 2 unitaries, this is simple. The fact that they anti-commute was quite hard. And also we showed that actually, if you take A0 plus A1 divided by square root of 2, you take the tensor product of this matrix with B0, and you act with it on the on the state psi. It is an eigenstate of this matrix with eigenvalue 1. Okay, so if you act with this matrix on this vector, it's like the identity acting on this vector. And the same thing holds for A0 minus A1 divided by square root of 2 tensor B1. So these two matrices share an eigenvector. This eigenvector is exactly the psi that they use, and this is an eigenvector with eigenvalue 1. Okay, so all of these conditions we showed last week, so I'm just going over them quite briefly. And then we said the following. So the fact that you have two matrices, let's call them for a moment. So I need two names of matrices, tau and sigma. Okay, so these are matrices. And you know that tau squared, so actually these are unitary matrices. So let's call it UN. So tau and sigma are in UN, and tau squared is equal to sigma squared is equal to the identity, and tau sigma is equal to minus sigma tau. You can automatically deduce that this is a representation, a representation of the dihedral group with 8 elements. So the isometries of the square inside the plane. And also, it's not any representation of this group. There's only one irreducible representation that satisfies this condition. So it's just the direct sum of all these representations. So you have the same representation repeated with a direct sum. So actually, up to some isometry, okay, so both the A0 and A1 and the B0 and B1 can be sent such that B0 goes to X tensor the identity and Z tensor the identity, and B1 goes to X tensor the identity, where X and Z are these two specific matrices. Because this is the representation of D4, the irreducible representation of D4, the single one that satisfies this condition. So the fact you take tensor the identity means that this is the fact that you take a sum of such irreducible representations, right? If you have a direct sum of irreducible representations, you want to act through all of them in this manner, okay? So thus B0 is Z tensor I and B1 is X tensor I. And actually we can send A0 and A1 to these two matrices. So A0, I send it to X plus Z divided by square root of 2 tensor I, and A1, I can send it to minus X plus Z divided by square root of 2 tensor I. So this is just taking two other matrices that give you the same irreducible representation. Yes, so this is just an isometry. But the point is, okay, so if you take this condition that psi is an eigenvalue of the tensor product of these two matrices, and also the tensor product of these two matrices, and you just put inside these values, so you just put Z tensor I instead of B0, X tensor I instead of B1, and so on and so on and so forth, it follows that actually if you act with the isometry that sends, like if you change bases such that B0 and B1 are actually these two matrices and A0 and A1 are actually these two matrices, you get that your psi was actually the EPR pair. I recall what the EPR pair was. So it was 1, 0, tensor 1, 0 plus 0, 1, tensor 0, 1 divided by square root of 2. This is EPR. So this is the only mutual eigenvector of X tensor X. You can check that this matrix now is Z tensor Z, and this matrix now tensor the identity, but we don't care about the identity part because we don't act on it. And the other one is X tensor X, tensor the identity. This is this matrix. And the only vector that is an eigenvector of both Z tensor Z and X tensor X is exactly the EPR pair, up to some unit constant, right? You can multiply by any element of the unit circle, but and you need unit vectors. So this is the only thing you can do. Great. Okay, so this was what we've done last time. And the consequence of all of this discussion, okay, so maybe I'll stay here for a moment. The consequence of all this discussion is that for the players to play optimally in this game, there is only one strategy that they can use. At the essence, there is only one strategy. They can only use these X's and Z's. The left player, the A player, can only use X and Z, and the right player can only use X plus Z divided by square root of 2 and minus X plus Z divided by square root of 2, and they must share an EPR pair. And if they share more qubits, you don't really care. Like you act only on the EPR part, and the matrices are just these matrices tensor the identity. Any questions about this part? No. Okay, great. So now I can define self-testing, because last time actually what we've done is throughout the lecture we prove the self-testing result. So a game, this is a property of a game. A game is a self-test if there is only one optimal strategy up to isometries. So exactly like here, you can apply some isometries on your space such that after you apply these isometries, the strategy is exactly a fixed strategy, which is unique. Okay, so again, you can share, you can force them to share more qubits, you can tensor with the identity, you can do these kinds of things, but this is the only things you can do. These are the only things you can do. Share non-used qubits and maybe tensor with the identity. Like, okay. So we saw that the CHSH game is actually a self-test for a single EPR pair. So the state that you're testing, they must use an EPR pair, and also they must use these X's and Z's under the conditions we showed in the previous slide. But okay, so for the completeness part, usually you have in these games, we want to say that if you win optimally, like with probability 1, the graph is colorable, right? Like this is the kind of statements that we have. And if you are, if the graph is not colorable, you cannot win with probability too high, right? So for the second part, you want also to say something about almost optimal strategies. Okay, you want some statement that says that actually in this game, not only that there is a unique optimal strategy, even almost optimal strategies are close in some sense, and I'll explain what is the some sense that they are close to this unique optimal strategy. So if you want to win with 99% probability, you actually only perturb, you take the optimal strategy, you change it only a bit, and then you get some strategy that wins with probability 99%. And this is the only way of getting a strategy that wins with this high of percentage. Okay, so for a game that has this property, a game that every nearly optimal strategy is close to the optimal strategy, is called a robust self-test. Okay, so we have a self-test, it has a unique optimal strategy, a robust self-test, every almost unique optimal strategy is close to the unique optimal strategy. Every almost optimal strategy is close to the unique optimal strategy. And my question now is the CHSH game robust in this sense? What was the question?
No, I just wanted, okay, yeah, thank you. And I just wanted to ask, like, whether these self-testing properties can be also, first of all, you are only talking about finite dimensional strategies here, right?
Yeah, everything is finite dimensional.
Okay, and like, can you also like, is it also relatable to like the game algebra? Like saying that a game is a self-test is saying something about the game algebra having a unique representation with some property, if you have heard of something like this. And because back then you said that.
I think this is the kind of argument that we've just done. Like the game algebra of the CHSH game should, but in this case, you don't have a perfect strategy. I need to think about it, okay?
Okay.
Maybe there is a way, like I presented it using representation theory of groups. Maybe there is a way of defining it using the representation theory of the algebras defined using the game that we talked about in the previous lectures. I'm not sure.
Okay, thank you.
Okay, but my question is the CHSH game robust? So, and my claim is that it is. Okay, so let me just sketch the proof. And it will be very similar to the proof that we had last time, but Now, instead of saying that everything is exact, saying that the probability is exactly the perfect one, the optimal one, and that the psi is an eigenvector of x tensor x and z tensor z and so on and so forth, we will see that everything will be approximately. And we will need to say in what sense, what is the approximation, what is the distance for which we use the approximation. Okay, so we assume that we have a strategy that wins with the optimal strategy, with the almost optimal strategy. So it's 1/2 plus 1/2 square root of 2 minus some epsilon. Now, next week, Alon will talk about Naimark's dilation. And Naimark's dilation tells you that every strategy you can enlarge your space. So assume that a priori they used maybe more qubits, but now all of their measurements are projective valued measures and not positive operator valued measures. So you totally disregard the case where these are positive operator valued measures. And actually in the proof that I used last week, I showed you that if they win with the optimal strategy, they must be projective valued measures. But in general, we usually don't care and we just assume that these are projective valued measures and we say using Naimark's dilation. So we do it, we apply Naimark's dilation on this strategy and we get some projective valued measures. Now the AIs and BIs that we defined are actually order 2 unitaries. Great, so these are order 2 unitaries. And let's recall the calculation from last time. So this number, okay, from last time. So let's recall that psi star C psi was exactly the 4 times the winning probability minus losing probability. Okay, so 2 square root 2 my psi star psi minus psi star C psi is just 2 square root 2 minus 4 times the winning probability minus the losing probability. Lose probability. Great, but what is the winning probability minus the losing probability? This is the winning probability. The losing probability is just, what do we get? We get 1/2 minus this 1/2 square root of 2. So we get 1 over square root of 2. So this is just, whoa. Okay, so everything is deleted here. So this is 2 square root of 2 plus 8 epsilon. I think I've done the calculation correctly. Okay, you can check that 4 times the winning probability minus the losing probability should be 8 times the epsilon. 2 square root 2 minus 8 times epsilon. So if you take 2 square root of 2, it's actually, this is the 4 times the winning probability minus the losing probability. And if you take 2 square root of 2 minus this number, you get 8 epsilon. Great, so this is the calculation here. And we used this decomposition last time. So we said that the C that we find last time actually decomposes as these two, the sum of squares of these matrices. And we can deduce from it that actually both the psi is almost in the kernel of this matrix and also almost in the kernel of this matrix, in the following sense, that if you take the norm of the image of this matrix acting on psi, it's smaller or equal to 4 epsilon. Okay, so this is a conclusion from this discussion. Okay, so this is just some conclusion, but let me show you now how you can deduce from that B0 and B1 almost anti-commute. And we need to say, what do we mean by almost anti-commute? Okay, so now notice that if you act with I tensor B0, B1 on psi, it's almost the same thing as acting with A0 minus A1I on psi, tensor B0 acting on psi, right? So I think of I tensor B0, B1 just as I tensor B0 times I tensor B1, okay? And acting on psi this thing by this an inequality is very near a naught minus a1 divided by square root of 2 tensor identity psi. So this is the first, almost the approximated thing here. And we can say that it is, okay, what can we say? These are unitaries, right? So actually, the distance between this vector and this vector is bounded away by 4 epsilon. This is exactly what we've shown here. And you can do it again, but now use this inequality, and then you get that this vector is at most 4 epsilon apart from this vector. And you can check that this vector actually equals this vector. And again, you have these approximately, so you get that I tensor B naught B1 plus B1 B naught acting on psi is bounded away from, I don't know, 16 epsilon. This is what we actually showed here. Okay, the norm of this thing is bounded from above by 16 epsilon. Okay, great. So we had this kind of calculation. So we have these matrices B naught and B1 that almost commute in the sense that if you take I and you tensor with this matrix and act with it on psi, it is almost 0. Note that this is the same as saying that B naught B1 plus B1 B naught, if you restrict it to the span of the VIs, right, in the SVD decomposition, this Schmidt decomposition that we talked about last time, and I recalled it here at the beginning, if you restrict yourself to span of VI, almost all of the span is in the kernel, is in the almost kernel of these matrices, right? Like this matrix sends almost all of this space very near 0, like to something that is bounded by the ball, this thing acting on each one of these vertices, of these vectors is bounded by the ball with radius 16 epsilon around 0, right? Like the unit ball of this span. Okay, great. Now I need to give you some claim, and I want to say something about this claim, at least as it is written here. It is quite elementary. Okay, so it can be a very hard exercise in linear algebra 2, but it is a possible exercise in linear algebra 2 for students. So nothing fancy is needed here, but in the next slide, I will say something which is much more fancy. So my claim is the following. If you have two matrices, B naught and B1, that satisfy exactly this condition, then there are unitary matrices that actually anti-commute, and also the distance between I tensor B naught and I tensor B prime naught acting on psi, and I tensor B1 and I tensor B prime 1 acting on psi is bounded away, bounded from C epsilon. Okay, and this C is universal. Okay, it's independent. It depends only on the, okay, it depends on nothing here. It depends on the group D4 actually, but for us, it's just a number. So what is the conclusion? The conclusion is if you replace, like I'm saying now something important. You show that you have two matrices that almost anti-commute. You can replace them but by matrices that actually anti-commute without changing much the role that they have in the strategy in the game. The way that they act on psi is exactly what we care about when we play the game. And actually, we don't change it that much. So they act almost the same on psi. And this is actually what I need, that if I replace the original B naught and B1 by the new B naught prime and B naught and B1 prime, I win with almost the same probability. This is the point. Like I won at first place with 1/2 plus 1/2 square root of 2 minus epsilon. Now I will win with some 1/2 plus 1/2 square root of 2 minus some constant time epsilon. And this constant is universal. I don't know, you can show it's 100 or something like that. But the good thing is now that instead of having almost commuting matrices, almost anti-commuting matrices, we have actually anti-commuting matrices. So we came back to the representation theoretic case. Now we have B naught and B naught prime and B1 prime that actually again are a representation of D4 and not any representation, the specific representation that we talked about before. And what you can deduce from that is that actually the psi that you used, the psi that they used in their strategy, it is not an eigenstate with eigenvalue 1 of x tensor x and z tensor z. So this is not true anymore, but it's an almost eigenvalue 1 in the sense that if you take psi star x tensor x psi, you need some identity, tensor identity, but you don't act on it. So I'm only looking at the part that is coming from x tensor x. It is almost 1. So it's greater or equal to 1 minus some constant time epsilon, maybe another constant times epsilon. But from that, since there's only one eigenvector with eigenvalue 1, so there's the eigenspace of 1 is of dimension 1, okay? You can deduce that actually this psi is very close to an EPR pair in the following sense, that psi is close to an EPR pair tensor some auxiliary vector, and this is exactly what we wanted to say. Okay, so this is the 2 norm. Here we had this funny norm. Notice that this is a very funny way of defining distance between matrices. I'm tensoring with the identity, and I'm checking that when you tensor with the identity, you act almost the same on the state vector that you started with. So this is a very weird definition of distance between matrices, but this is actually the definition that we need. So in conclusion, we saw that you can start with an almost optimal strategy. You can take some isometries, you maybe enlarge the space, and the only point that we enlarged the space was replacing the POVMs with PVMs using Naimark's dilation. So we changed the fact that we use positive operator valued measures, and we now use projective operator valued projective valued measures. And this maybe enlarged the space, but except that we didn't need any embedding. And up to this embedding, we know that actually there are 2 embeddings here. So I wrote that there's an embedding on the left side and an embedding on the right side, such that when you act with these embeddings, your psi is very close when you embed it. It's very close to the EPR pair tensor the auxiliary. And if you take this matrix, so if you embed, act with your A naught, this is what we called A naught, and then you take the co-isometry of your isometry, maybe I needed the other way around. I think I wrote it the other way around. Okay, so I think you should do A naught and take minus X tensor I, and here you need to write V on the right and V star on the left. I think now this is the correct way. And my claim is that this thing acts on psi. The norm of this thing acting on psi is very close. Okay, so here I need another tensor with I. So this is tensored with I. This is tensored with I. I'm sorry, there are many tensors with I. This is smaller or equal to some function of epsilon. And again, this function is linear in epsilon, and the constant in this linear function is just depending on epsilon, on the group D4. So it's a universal constant. Okay, so I'm summarizing. CHSH, to win this game with almost optimal strategy, implies that up to this weird way of checking whether 2 matrices are close to one another, you are close to the unique strategy that we showed is the only optimal strategy for this game. Okay, now any questions about this part? Like I'm a bit not sure whether you're with me.
Can you please again explain what is this measure of closeness? Like you
I'll do it in the next.
equation.
I'll do it in the next slide. But for now, it's just I'm claiming that I tensor B naught minus I tensor B prime naught acts on psi. So psi is an almost is almost in the kernel of the difference of these two matrices. Okay, this is bounded by some constant times epsilon.
Mm-hmm.
So what did you do that was very particular, that is not general? Which specific properties helped us?
Okay, so we need a group with such that your game forces you to use a single representation of this group. So you need to have this unique representation of the group that satisfy this relation that actually is a matrix relation, right? In groups, there is no sense of being anti-commuting. There is no -1 in groups.
True.
A priori. You can add a -1, but there is no -1 a priori. Right. But the point is that if you know that you send -1 to -1, so you add a generator, you add a central element that you call -1, and you check that this -1 is actually sent to the matrix minus the identity, and this forces you to use a specific representation of your group. This is what enables you to have this kind of magic, that you have a unique strategy for winning. So in this sense, this was very particular to D4.
Okay.
Possibly there are other, so I will show you that there are other groups that have this property, but they are just powers of D4. So in some sense, I don't know of any interesting example that is not D4.
Oh, good.
Okay, so we saw that every almost optimal strategy is an optimal strategy. So let me tell you something about stability theory in groups. So first I want to define what Alon asked, like what is the distance that I'm talking about. So now I'm saying that define a weird kind of norm. Yeah.
I just want to comment about Nati's question, which I'm not sure I understand. I mean, Nati asked what is particular about this, but I'm not sure what this means. Something that is particular here is that all these M's, all these the fact that you had such a simple expression for the success probability in terms of the matrices is, I don't know if it's a miracle or if someone designed it, but it's something very particular to this game. You could probably do something similar for any game, but then you would need higher powers of like the A's and the B's were defined with, as just a linear function in the POVM matrices. For general games, I guess you would need higher powers, and I don't know what would happen then.
So we will see that next, that there is a very rich family of games for which you can do similar things. But
answering Guy's question, I mean, you want me to be a bit more concrete. So under what circumstances can we say that if two matrices almost anti-commute, then they can be slightly modified to get two matrices that anti-commute?
Okay, so here you use also the fact that these are order 2 matrices.
Okay.
You are already given that these are order 2 matrices. In general, this is not true. Like, I don't think that this is true in general.
Anti-commutation. That's interesting.
Yeah, whether stability of anti-commutation. Alex, You are with us? I'm not sure.
Wait.
Only his picture.
This is the property of stability of an algebra, but the universal.
Yeah, so this is a very interesting question, Nati. Like whether, if you don't know even whether they are order 2, only that they are unitaries and they almost anti-commute, can you deduce that they actually anti-commute? I'm not sure. Like for commutation, using the operator norm, for commutation, this is just not true. You can find almost commuting matrices in the sense that AB minus BA is close in the operator norm to the 0th matrix, without A being close to some A prime and B being close to some B prime, such that A prime and B prime actually commute. But for anti-commutation, I'm not sure.
But here we are talking about not something very different from the operator norm.
Right. This is not the operator norm. So the point here is that you have some other norm here, this weird norm that I'm just talking about. And using this norm, you can have, you know, this kind of result on all finite groups. So for general anti-commutation, I'm not sure what can you say, but at least for finite groups, I can tell you that every finite group is stable with respect to this norm, and I'll just state what does it mean. So let's just say that the psi norm of a matrix is taking, recall that psi is in C to the D, tensor C to the D, right? So you take X as the matrix acting on the right coordinates, you take the identity on the left coordinates, you check what is the norm of the vector when you act with this matrix on psi, and you call it the psi norm of the state norm, the state dependent norm of this X. Okay, so this is the definition of the state dependent distance, because if you take the difference between two matrices, this is the distance between these matrices. And a very, at least in our circles, famous result of Gowers and Khatami, and then a conclusion like Natarajan and Vidic modified Gowers and Khatami's result to the specific case where you use this specific norm. So this specific norm is very close to what's called the Hilbert-Schmidt norm, if you know what the Hilbert-Schmidt norm is, and the normalized Hilbert-Schmidt norm. And actually, Natarajan and Vidic showed that you can just use Gowers-Khatami and apply it to this specific norm, this specific state-dependent distance. And what it shows is the following. So we defined those epsilon representations for algebras. So an epsilon representation of a group is just the same thing, okay? So the relations are almost satisfied for the relations that you wrote for this group. And the point is that if you take any finite group, there exists some, someone muted me. So I'll say it again. There exists an actual unitary representation of G. Okay, so you say that you start with an epsilon representation. My claim is that there is an actual unitary representation on maybe a larger space. Okay, so this unitary representation is on C to the n, large n, and C to the small n is potentially smaller, but there is some isometry that satisfies the following. If you embed these sigma i's, if you take any, okay, so the way you should think of it is something like you have your vector, you embed it in the large space, you act with the actual representation, and then you push back the vector to the original C to the small n. This matrix, okay, so this defines some operation. This operation is some matrix inside, this thing is inside M small n C. And the point is that this is very close to the generators that we started with. So in some sense, every almost representation, every epsilon representation comes from this process of embedding your space in some larger space, acting with a genuine representation, and then pushing down back to the original space. Okay? So every epsilon representation is close to this process. Okay, so it's not actually this process, it's close to this process under this psi norm, under this state-dependent distance. Okay, so this is a bit of a mouthful, but this means that actually D4 is not, we had this claim. If you have matrices that almost anti-commute and of order 2, there are actually anti-commuting order 2 matrices that are close by in this sense. The point is that you can replace the order 2 anti-commuting condition by any set of conditions that generate a finite group. Okay, this is the point. So if you have a set of relations, set of matrices that almost satisfy a set of relations that comes from the relations of some finite group, I'm not reading the chat, so if anything is
yes, there was a brief discussion just about your comment, like for the operator norm, this is not true, like for commutation, for the commutation relation,
okay.
but for
no, I don't want to go back.
It's just to clear up what you said before.
Okay, great. So the point is that for any finite group, this is true. You can fix any almost representation of a finite group to an actual representation of a finite group using this metric, this psi, this state-dependent metric, okay? And I'm reminding you what is our goal. Our goal, and I will finish by that this part of the talk, the first hour. We want to test many EPR pairs. Okay, so we just checked that we forced, if we play the CHSH game, we force the players to share a single EPR pair. But we wanted them to share exponentially many EPR pairs. So the goal at the beginning of the next hour is to use this Gowers-Khatami machinery and force the players to share for at least polynomially many EPR pairs. Okay, so this is the slide, and I will talk about it at the second hour. So I'm here, you can, we are having a break.
10 minutes, 15 minutes? How
yeah, up till 5. We will resume at 5.
Michael, I have to leave. I have a meeting, so I won't be here at the next hour. Sorry.
Thanks. Okay.
Oh, but you should say one thing, that you need to enlarge the dimension, because if you take a unitary representation, just erase.
I wrote that you need to enlarge the dimension.
No, yes, but just the example that this has to be, not that there's a simple example. If you take a big unitary representation, just erase the last row and column, then you get something of dimension n-1, which is almost okay.
Right. So for larger and larger irreducible representations, so if you have a group with as large as you want irreducible representation, what you just showed is that you cannot expect it to be fixed using the same dimensions, right?
Yeah.
But for example, if your groups are all a billion, you can expect like all the irreducible representations are just 1 by 1, right? So you need to say something about the groups, and for the family of all finite groups, you can have larger and larger irreducible representations, and this is why you need this enlargement, as you said. If you want a constant that doesn't depend on the group, the point is that our constant from before, the delta epsilon, did not depend on the group.
I don't think that Khatami and Gowers get constant enlargement. No.
The constant enlargement is in the distance, the distance of the
dimension.
The dimension they get 1 plus epsilon.
1 plus epsilon.
Yeah, one like n, small n is very close to large n.
No.
But for our applications, it's unnecessary.
Yeah.
Yeah.
Okay. Bye. Sorry.
Bye, Michael.
Michael Chapman, I want to continue maybe asking, so you here want to consider stability of all finite groups together? This is the point where
Actually,
while enlarging the
I
dimension?
bit lied because I want for all finite
I
groups
see.
a specific representation, but I just wanted to give the idea.
Okay.
Actually, we need, and I think you need this delta. Okay, so I can say something a bit more precise. This delta doesn't depend only on epsilon. It depends also on the diameter of the Cayley graph of your representation, of your presentation. So take the Cayley graph of G using these generators. It has some diameter. So this delta is a function also of this diameter.
Mm-hmm.
So as long as you bound your diameter by some constant, and all of our, for example, in Gauss and Khatami, actually they take the generators of the group to be, the generators to be all the group elements, and the relations to be the multiplication table of the group.
Mm-hmm.
Alon, you are with me?
Yes.
Yeah, so they take S to be all of G and R to be the multiplication table. If you want to generalize it to general presentations, you need to say something about the diameter of the Cayley graph, and I didn't say anything about the diameter of the Cayley graph, but you should. But I will always take presentations of finite groups that have a bounded diameter.
So they're working with a complete graph.
Yeah, they work with the complete
Gauss
graph,
Khatami
exactly.
is complete.
Yeah, even with loops, right?
Mm.
They also take the identity. It's not important, but they do. And this is something called an epsilon homomorphism, but I'm not getting into it. You can just think of it as an epsilon representation of the group with a specific set of generators and relations. נתי זה רק שנינו.
יאללה, בוא נתחיל, נגמור את כל החומר ב5 דקות, ונלך הביתה. בעצם אנחנו כבר בבית.
אני לא, נראה לך.
אתה לא בבית? אתה באוניברסיטה?
רגע.
איפה אתה? אוקיי, נחשפת.
במשרדי.
אצלנו אומרים בלשכתי. דווקא הילדים שלי שהם היו קטנים, לימדתי אותם את הדעה הזאת. אני מתייחס לחדר ילדים בתור לשכתכם. עד שישאר אותו.
Okay, guys. Hopefully you are here. I'll resume the talk. Okay, so let's recall again. Oops. Stop sharing and reshare again.
Michael, you said that
Yes.
that for the case of the dihedral group, this Gowers Hatami Natarajan Vedic thing is an exercise.
Yeah, this is true. This is true.
But
At least for D4, it's an exercise.
So why is it not an exercise for any group? So you really need to use the dihedralness for it to be an exercise?
Yeah, exactly, because when you have two order 2 matrices that almost anti-commute, you can say something about the bases for which you, okay, so these are order 2 unitaries, right?
Mm-hmm.
So these are not involutions. We had this name last time. These are also involutions, but shikufim.
Reflections.
Yeah, these are reflections, and if you use the fact that these are reflections, you can somehow deduce this. Okay, like this is generic linear algebra. I can send you. Vidic has some course notes in which he gives this algebraic trick that enables you to prove it at least for D4 in a straightforward manner. As I said, a hard exercise, but a possible exercise for a student doing linear algebra too.
Mm-hmm.
But for the general groups, you need some generalization of the Fourier transform. Okay, so this is actually what you need. Alex, we had, you're hearing us? We had a small question before. I said that I know that at least for the operator norm, the fact that two matrices commute, almost commute, doesn't mean that they actually commute.
Yeah.
Can you say something about anti-commutation in the operator norm?
So anti-commutation means what? That AB
plus BA. So the plus
equals minus BA.
So you think of it, but still unitary?
Yeah, for example,
yes.
still unitary. Yes, still unitary.
You can think of it as a central extension. Yeah, so I think the answer is no for the operator norm. I think because you see, you can think of it in the following way. Think of it as a Eisenberg. Take the Eisenberg group,
Okay.
and then so you can think of it as a representation of the Eisenberg group. If the Eisenberg group is like, think of it as X, Y, and Z. Z
Right.
is the general for the center.
And XY plus YX is exactly what you.
But I think if I'm not mistaken, what you are talking about here is that X, is it the same as X as a representation of the group X, Y, Z, and Z square equal 1? Is it the same or not? If this is a representation of this group, then I know to prove that the answer is no. Now let's see. Because it's an additive relation, I'm a bit confused for a minute. If this can be translated.
Yeah, exactly. It's not.
No, but if you take AB, so AB is equal minus BA, right? So
almost equal in the operator norm. Almost equals, yeah, in the operator norm.
No, yeah, okay, but AB, if it would be equal, it would be AB equal minus BA. You can take B and A to the other side. So this is like the commutator is equal minus 1.
Right.
Okay, so that's okay. So this is a representation of this Heisenberg group. And for the Heisenberg group, I know that the answer, and even for that group, the answer is negative. And you will, I don't know an easy proof, but you will see it in my seminar at the Institute in the next semester by the results of Dalla Art. Once you have a group which has a second trivial cohomology with trivial coefficients, then it does not have in the operator norm, and the only direct proof the only proof I know goes to vector bundles, and it's very complicated.
Can you mention the name again?
Okay.
But I'm sure that for this special case, I'm pretty sure that for this special case, one can really do it by ends because it's a very, very simple
equation. Yeah. So okay. So Nati, I think it answers at least. Alex, I'm stopping you for a moment. I'm saying that the point I think of what Alex just said is that these kinds of results are very hard. And this also answers Guy's question. So even this Gauer's Khatami result.
Let me be, I don't think that, no. I mean, because you asked me, maybe I'm bringing an elephant which is not really needed. I'm not completely sure, but that's what I can answer right away, applying all the kind of machinery in the world that I know. But I have the feeling that for this specific case, you probably can do with Vasculescu something, take the counter example of Vasculescu for XY equal YZ, and there is a good chance that already this will give you something.
What is this example? I see that also Gulnara mentioned it in the chat.
There are two matrices. I think I can even recall them. Take the diagonal matrix, take a zeta to be a primitive nth root of unity, and take the matrix 1 zeta square, blah, 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 up to zeta to the n minus 1. And take, so this is one matrix, and the other one is the shift on the basis.
Okay.
Right? EI goes to EI plus 1, etc. Take these two matrices.
The matrix that goes zeta squared, and then at the end 1?
No. So this is one matrix. The other one is
just a rotation.
It's just a rotation on the basis.
The super diagonal.
Right. Now take these two matrices, and then you can see that the commutator of them is a scalar matrix, which gives you on the diagonal zeta.
Right.
And therefore, if n goes to infinity, this goes to 1. So these are almost representations in the operator norm. And the non-trivial part of a Vasculescu result is that it's not close to any representation of Z cross Z. It's a very beautiful argument. I don't know if that's the original one. There is an argument called by the winding number. It's a nice. now the group we are talking about is just kind of a central extension by a group of order 2 of that group. So I won't be surprised if you can do just some kind of a small twisting in this argument of Pascal. Yeah, maybe I can even suggest one. If you take, maybe if you take Vascalesco examples and you take one minus zeta, zeta square minus zeta. Oh no, that's not.
Okay, Alex, I think maybe this is a good discussion, but
okay, sorry, I mean I didn't want, but I'm pretty sure that this one that there are representations like that in the operator, no, but not in the Hilbert-Schmidt.
Michael, I will stick one more second. It seems to me that as an outsider, I don't work on these things. It would be very interesting to understand, to classify the equations which do and don't have this stability condition. Seems to me like a very
Nati, come to my seminar. That's the whole topic.
Okay, very good. Except what hour is it?
But let me just say one sentence, and we let Michael to talk. The whole point here, that you can, if starting with a set of relations, like equations, you can associate a group to them, an abstract group gamma, which is, say, finitely presented group, and the stability of the equation does not really depend on the equation, but depends only on the group. Namely, if two systems of equations give rise to the same group, then everything depends just on the group and not on the equation. So this makes it into a group theoretical problem about the group gamma. And for every such group gamma, you can ask this question with respect to the operator, with respect to that, with respect to that. So there is a rich theory here that some of us are working in the last couple of years to develop.
Okay, thanks, Alex.
Michael, if you don't capture the right to talk, they won't let you.
Yeah, so I'll do it now. I just want to mention that our two matrices, the Z matrix and the X matrix, are just the two-dimensional example of Alex's what Voiculescu used, and actually there are quantum information theoretical papers that use exactly the definition that Alex took, like taking the unit elements on the diagonal and on the the rotation matrix as the other matrix, and this is an important pair of matrices that we are also going to talk about also in the general case. So this was just a teaser. Anyway, we tested a single EPR pair. Now we have this stability, the Gauer stability, the Gauer-Khatami stability result that Natarajan and Vidic generalized to this weird state-dependent distance. And the way you take the EPR pair, the single EPR pair, and you generalize it to many EPR pairs is just using the group D4 to the N. Okay, so I'm going to give you a specific presentation of D4 to the N. So it's known that in D4 to the N, there are two copies of F2 to the N, of the vector space F2 to the N. And I call these two copies, one of them I call it X to the V for any V in F2 to the N. And then the other I call Z to the V for any V in F2 to the N. So these are the X to the V and Z to the W here. And there's a single element will be an order 2 central element that I'm calling -1. And I will ask you to send -1 to -1. And you use the following relations on this group. So I stated that if you choose W is either X or Z. Okay, so W is just or X, both of them are or X.
But it's not the W that appears as a subscript and superscript.
Right, this is large W, and the small w is the one appearing. I see that it's a bit confusing. This w is either an x or a z. So the point is that if you multiply x to the v by x to the v prime, you get x to the v plus v prime. This just checks, and everything is of order 2. So everything, I didn't write it down, is of order 2. Not only the central element, or everything here is of order 2. All the x's, all of these things are of order 2. So this relation just checks that actually all the x to the v's and all the z to the v's are copies of the nth dimensional vector space over the field with 2 elements. So this is this relation. And you have this skew, this weird skew commutation relation, which states that if you multiply x to the v by z to the w, it's exactly the same as z to the w times x to the v, but you need to take -1 to some power. What is this power? So v dot w is just the dot product of v and w. So you chose some basis. Okay, so this is just vi wi sum modulo 2. Right, the vi's and wi's are just plus zeros and ones. You take the multiplication of them, you sum it up, you take mod 2. This is what's defining whether they are commuting or not commuting. So if you don't believe me, you can check that actually this is a presentation of the nth power of the dihedral group of D4. Okay, and now how can you test? My claim is that you can test these relations.
You deliberately don't say the Pauli group?
I can say, I think it's the Pauli group. It's part of the Heisenberg group, maybe? No, not Heisenberg.
The Pauli group, maybe with
modulus without the y,
maybe modulo some scalar or
modulo
something.
I, yeah, modulo I, right?
Yeah.
It is the Pauli group modulo something. I don't remember what, but since I'm more used to the dihedral group, I call it that way. But yeah, this is the nth dimensional Pauli group. How would you call it?
The Pauli group on n qubits.
On n qubits, thanks. The Pauli groups on the Pauli group on n qubits. Right. Okay, so maybe I'll call it Pauli group on n qubits. Thanks. Actually, this is a good point. Okay, but it's just the previous group that I took to the power of n. Now my claim is that you can define a self-test, and quite amazingly, this self-test is robust. Okay, in the previous sense, for this group. How do you do it? There are actually 3 kinds of relations here. Either you check this linear relation, or you check this relation when it's an anti-commutation relation, when this power is 1, or you have this relation when this power is a 0. Okay? So for any 2 generators that you give me, you can just uniformly choose 2 generators. If both of them are x's or both of them are z's, you check whether they satisfy this linear condition. Okay? If one of them is an x and the other one is a z, you check this skew anti-commutation relation. If it's a commutation, you check its commutation, and if it's anti-commutation, you check anti-commutation. Now, you should ask me, how can we check these relations? So at least for the anti-commutation relation, we can play the CHSH game. You agree with me that if I want to check that these matrices anti-commute, I can force the players to play the CHSH game with me using these 2 matrices, and there is a way of doing that. And by that, if they win with optimal probability, these matrices must anti-commute. Okay, this part was clear. So at least this part, we know how to do. For linearity, there's a very famous test called the BLR test, okay? The Bloom-Luby-Rubenfeld, right? that checks linearity. Okay, so if I need to check this thing, I'm just playing the linearity, the BLR test. So I'm playing a game that simulates the BLR test with the players. Okay, and by that I'm checking this relation. Okay, now the BLR linearity test is a very what, Guy? You want to say
Yeah, I have a question about the previous item. So you're describing a game, right? A two-player game.
Yeah. Yes.
Okay. So, and the, I don't know, the house, the one that picks the questions.
Right.
Referee.
What?
Referee.
Sorry,
Yeah, the
Dorit?
referee. Dorit said the referee.
Okay, yeah. The referee picks two generators, and they could be an X generator and a Z generator. And
Right.
if they are an X and Z two X and Z generators that are supposed to anti-commute, you
Right.
said use CHSH, but I'm not sure I understand what this means. Like, what
Yeah, so
they
there is some, you are correct that I'm sending questions of the form X, V, or Z, W. These are possible questions to the players, and I can maybe even send few of them. Okay, so I can, for example, send to one player XV and XV prime, and to the other player I will send XV plus V prime. Okay, and what does it mean that I play the BLR test with them? It means exactly that this player needs to give me 2 bits. This player needs to give me a single bit, and the bit that this player gives me needs to be the sum of the 2 other bits that I got. Okay? But since the answers to the CHSH game are the same, they are just single bits, right, Kai?
Yeah.
I can actually send to one of them these kinds of questions, and to the other, like I can tell them just these kinds of things. And when I say X and Z that's supposed to anti-commute, I just check that they satisfy the CHSH conditions, okay? But they still answer with a single bit, right? And when I send these kinds of questions, I check linearity, which means that I play the BLR test with them. And actually, there's another thing called the commutation game that I'm not going to talk about right now. That there is a way of an even simpler test, simpler than both the linearity, the BLR and the CHSH games. That's called the commutation game, and you can again just send something like 2 questions to one of them, a single question to the other, and all of the questions are of this form. Okay, and they answer only using bits, and if they pass the test with optimal probability, it actually means that the matrices that they used to play this game are a representation of D4 to the N. Okay, like this was a very good question. I hope that like Guy asked a very good question, and I think I explained how do you play such a game that checks every one of these conditions. So this is the kind of thing, and the point is that at least to win optimally in this game, it's clearly that you need to have a representation of D4 to the N. What's not clear here is that it's a robust self-test. The fact that it is a self-test, this is easy. The fact that it is a robust self-test, this is very not easy. Okay, so you need to show something, but this is a result of Gowers and Khatami. If you use the theorem that I gave you in the previous slides of Gowers and Khatami and the modification of Natarajan and Vidic, you can actually do some analysis and get this result. Okay, but again, this only verifies that the players use n EPR pairs. Okay, so the n here is exactly the number of EPR pairs that they need to use to win their the game with optimal probability. Okay, but we wanted exponentially many, and here there is a wonderful trick. Okay, so I think this is an amazing thing. What is actually the BLR test? The BLR test is taking
Michael, can I stop you just for a second? Before that, can you go back to the previous slide? So basically, the idea is that you pick a random relation out of the exponentially many relations.
Yes, right. But you think of picking two elements, right?
Yes,
I think
but,
you should.
But there are exponentially many choices.
Yes, this is true.
Okay, and then the claim is that with this test, what is the probability that you actually detect? So how robust is it? How many, or actually how many tests do you need to run in order to?
It's a constant. Like you can say that if you are epsilon, for any constant epsilon, if you epsilon almost win with optimal probability, you are some polynomial of epsilon close to an optimal the optimal strategy. So the best a constant robustness.
So basically, if you randomly choose some I don't know 90% or 99% of the relations, then the closest group that satisfies all these relations would be the only group that satisfies these relations would be the Pauli group.
Say it again. Maybe I'm missing something in your question.
Dorit,
well, when you randomly choose a relation, and you're saying that with high probability you will actually be, if it's satisfied, you will actually be close to the right group. What that actually means is that you don't actually need to check all relations. You only need to check a fraction of the relations in order to be sure that you're close to the group.
Well,
yeah, I understand what you're saying. But when I'm saying, okay, let's leave for a moment. Yes. Yeah. Okay, so there is some expectation thing here. Clearly, okay. So Dorit, you said something very true. This is a very redundant presentation, right?
Yeah.
So actually, to generate this specific group, you need much, like you need like this is to generate D4 to the n, you need only 2n generators, but here you have 2 times 2 to the n generators. So yeah, it's very redundant in this sense. At least winning optimally clearly means that you have a representation of the group. Okay, this is clear, right? But the unclear thing that you just stated, which is true, is that if with expectation, when you check these relations with high expectation, you win, it means that you are close in this state-dependent distance to a representation of this group. Yeah, so this is exactly Gauss and Khatami.
Okay.
Which, as you said, is not very obvious. But there is some, you need some expectation here over questions that I hid in the previous slide. So actually, okay, so there is some probability here, but I'm leaving it now. Okay, great. As I said, now I want to somehow at least give you the feeling of how you go from a polynomial amount of EPR pairs to exponentially many. And this is using error correcting codes. So what is the BLR test? This is a bit, this part of the lecture is a bit for experts. So hopefully there are at least like, I know that there are at least half of you know what is the BLR test. So I'm feeling a bit that I'm allowed to talk about this point. So what is the BLR test? Actually, it's taking a vector encoding it using the Hadamard code of this vector. So taking all the inner products of this vector with any vector of your space. And this is your encoding. So you enlarged, you took a vector which is of size n, you encoded it using a huge vector, 2 to the n sized vector. But what's good about this code is that it is locally testable. And the BLR test is exactly what's checking locally that this word is part, like checking whether this word is part of the code is possible by checking only a small part of the code. This is what it means to be locally testable. So the BLR test means that you use the Hadamard code, which has bad rate. The idea, the way of moving from polynomially many qubits, EPR pairs, to exponentially many EPR pairs is replacing the Hadamard code with the Reed-Muller code, which is still locally testable, but has much better rate. And at the 20th of December, we will have a talk. Amnon Tashma will give us a talk about Reed-Muller codes. So what I just stated will be more concrete when we talk about Reed-Muller codes. But the point is that the fact that you enlarged the rate and you replace all the BLR tests with low degree tests, so you check that some polynomials are of low degree, allows you to somehow verify that the players are using an almost representation of D4 to the 2 to the n, okay? So this is the magic trick, and technically this is very, very hard. And I'll say even more, the error in the proof that was corrected just before the semester started was in this kinds of, like not in this specific part, not in this specific paper, but this paper, the paper that proved this point is one of the essential points that fall apart when the mistake was found, that fell apart when the mistake was found, and they corrected the mistake by exactly somehow fixing this Reed-Muller, these low degree tests. So they had a problem with the low degree test, the soundness of these low degree tests, but they fixed it. And now they can still deduce the fact that they use exponentially many EPR pairs. But my point in what I just said now is that it's technically very hard to show that this.
Can we state the theorem?
What? Say again?
There is a theorem here that you allude to.
Yes, the theorem is that instead of using BLR, use some low degree tests. Don't take any generator of this form. Take only polynomially many. Like now you want to check D4 to the 2 to the n, right?
Mm-hmm.
So you bundle up generators in such a way that it is very compatible with low degree tests, okay? These kinds of line versus point, plane versus points tests, okay? And somehow by only checking now much fewer, like Dorit asked about checking very few, like just a few relations out of this group. The point is you now check exponentially less many, like logarithmically more, I don't know how to call it, like you reduce the, by a logarithm, the amount of relations that you actually check, and you still get the same result. So you can still check that you have a representation that your, the observables, the strategy, if you take these AIs that I defined before and BIs, actually they generate an almost representation of this group. Okay, and then you can use Gowers-Khatami. It's okay, actually this is not known to be a result of Gowers-Khatami. This is much like you cannot use Gowers-Khatami here. You need something stronger, and they prove something stronger. Like this is highly technical. My point is just this point is something like 100 and something pages out of their papers. So.
No, but I understand, but I don't really understand. You know, you give some sense of what's happening.
Okay, the BLR is a local. Yeah, my claim is that if the BLR is the local test for the Hadamard code, Nati, there is a way to replace it with the local test to the Reed-Muller code. And somehow you still check that you are close to a representation of D4 to the n, but now instead of D4 to the n, it's D4 to the 2 to the n. This is the way that replacing.
This is, what is underlying it? It's a theorem about a code that is really an error correcting code that works fantastically. And what's happening?
You need to show that all these tests are sound against. Okay, so first of all, you need to show some soundness results of these tests. You need to show that these tests actually are sound against quantum provers. Okay, this is one part. But the other part is exactly saying something like, you checked only a really small fraction of the relations of this group D4 to the 2 to the n, but still you could have deduced that this is the group that they use, okay? So the way they do it is, I can maybe prepare a talk about this proof. I can maybe do such a talk, but I think we will wait at least for the second semester, and then I'll prepare something very
I just wonder, what kind of animal is this? Is this a type of a PCP that you really check? I mean,
no, it's not.
Can I ask something?
This cartoon of the Far Side, and these two professors with a beard, and then the magic happens, and I mean, but tell me what magic, what kind of magic is happening?
The magic is exactly.
Let me just add to Nati's question. Basically, what it shows is that there exists a subset, which is extremely small, of the exponentially many choices of the relations, which is still sufficient to sample from and deduce that the group is close to what we want.
Yeah,
now,
and in some sense, these are not these relations, because these relations comes from the BLR test. We see that here there is the BLR test, right? Dorit, my point is that you need to replace this relation and actually some of the generators such that it is more compatible with low degree tests, and then what the property that you just said applies.
Okay, but the question, I think, is, for example, one source for the reason for this is that somehow these relations, the set of relations that they decide to focus on, is such that any other relation is close in some sense. It can be generated from that in a short way. And then the error accumulated is not too large, and then everything would work in some kind of an expansion.
Yeah, so in this, I think it's the diameter of the Cayley graph, Dorit, what you just said. If you take the Cayley graph of this group, the diameter is 2, I think. Maybe, yes, if you take -1, x to the v, z to the w, every element of D4 to the n is just either x to the v, z to the w, or z to the w, x to the v, right? Maybe with plus minus. So the diameter of this, the Cayley graph of this thing is very small. So if at each edge you lose just a small amount of information, the fact that you can move around your graph very quickly means that you don't accumulate lots of.
But is this the source of the proof? That you actually get?
This is part of Gauer's Khatami, actually.
No, I'm asking, I'm continuing Nati's question. Is the source
Yeah, I understand. I cannot say for sure that this is the source, because this is something you need. You need in some sense that the analog, the Cayley graph for the analog representation still has a very small diameter, so you can still move around very quickly and don't accumulate very many errors during your path. But I don't see from the proof that they gave exactly what you said. Like I see it as, I don't see why this is enough. Okay, they do something much like it is quite amazing what they are doing. They somehow combining the check on the Reed-Muller on the left side and on the right side to something larger, and then they somehow linearize everything, and it's technically there are many ideas there. I cannot just say, yeah, it's like having a Cayley graph with small diameter, or this point or that point is just automatically giving you the proof. It's a very involved proof. I don't know whether
Michael,
it's...
I'm not asking, no, I understand it's technically extremely complicated, but I still don't understand what is, they do a miracle, but what is, you know, they draw water off the rock, you know, what do they do?
They define a test, Nati, a game.
Okay.
They define a game. And they show that this game has polynomially many, the size of the questions is polynomial, the size of the answers are polynomial, and the conclusion is that to win this game with almost optimal probability, you need exponentially entanglement of exponential dimension. This is like the result. And the way they do it, I thought that I gave you more information about how they do it. They use representation theory of D4 to the 2 to the n, and they check relations. The game is based on checking relations out of this group. But now, instead of checking these linear relations, which are not very efficient because the Hadamard code is not very efficient rate-wise, you replace it by Reed-Muller codes. So they are somehow able to replace these relations, but by more efficient relations to check that allow them to move to checking the representation of this huge group instead of this smaller group, D4 to the n that I showed.
You make it sound as if this is completely within a classical part of the proof, because you replace BLR with
yeah, but you need to check that everything is sound against quantum provers. So lots of the technical issues is the fact that you are against quantum provers.
Okay,
right?
but do you know if you just want to be sound against classical provers, is it possible to just say what you, is it trivial, or is it like there is a classical
strategy that wins with 100%. So in this sense,
I mean, it sounds like what you're saying is that there is an extension of BLR or an improvement of BLR for this classical.
No, but they use something very quantum, like the fact that the local test, they somehow use the okay, first of all, they use CHSH, which is highly not classical, right?
Yeah.
No,
so
but
automatically they must use no, but the end result clearly BLR tests for F2 to the n, right, Dorit?
Sorry?
BLR tests for F2 to the n.
Right.
Tests that you define some homomorphism from F to the n to F2, right? So this part is actually classical, but for them to win the game, they need also to win this quantum part.
Yeah, this is clear.
This forces them to use specific, very large representations of F2 to the n, right? They can use like very, I don't know how to say it.
I guess the question can be asked, of course they need CHSH game, this is a quantum result. You cannot get around that, but
yeah, right.
I guess this question is whether this Reed-Muller trick cannot be stated classically because it focuses on the BLR test.
I think, Dorit, there's this result of Ito and Vidic, right?
Mm-hmm.
That MIT star contains NEXP. And what is the gist of the proof is that they take the classical test and they say, okay, it's also sound against quantum provers, right? So you can think of this part as something similar. You take the low degree tests that come from the classical Reed-Muller codes, and you show that they are sound against quantum provers. And in this context, they can show that actually if you aggregate both what you get from this, now it's the analog of the BLR, like the local tests for the Reed-Muller code, and they don't actually use the CHSH, they use the magic square, but we don't care for now. Some anti-commutation test and this commutation game, if you aggregate all of these things, they get a representation of D4 to the 2 to the n. This is my point. you take some classical tests and some tests that are only relevant for quantum provers. And if you aggregate everything together, you get a representation of this group. And they do it by steps. They take the observables that they start with, and they show that they have some relations, and they generate some, and they show that if you manipulate them in some ways, you get observables that that are local tests for some larger Reed-Muller code. So at some point they enlarge the Reed-Muller code, and then from that they can push it back down again and get a representation for d4 to the 2 to the n. So I can just say again and again like that I can give maybe more details about the technical, but I don't see I don't see anything more quantum than saying that they play the CHSH game sometimes, and this forces the provers to somehow behave differently. I don't know.
We will probably understand it better.
Yeah, I will prepare it for the next semester. We will not do it this semester, but we'll do it at the beginning of next semester, and I'll bring all the details. So hopefully you will have some insight, because at least I don't see anything deeper than what I said now.
Can I ask like several very technical, down-to-earth questions? So when you go from this BLR test to the low degree test,
yes,
you can keep the other slide. The questions, are they still are the questions a subset of the questions that are in this slide, or are
no. The questions are much more. The questions come from the local tests to, like, the answers become, instead of single bits here, all the answers. Let me say something about the answers, not about the questions. All the answers here are single bits or 2 bits, right? Mm-hmm. In the local tests for the Reed-Muller codes, you need polynomials as answers. So the answers are much larger. Okay. And similarly, the questions potentially are much larger. You need to give lines, you need to give maybe planes, you need to give some affine spaces of your vector space. So, and actually you need to work not over F2, you need to work over F2 to the K for some K, like you need some larger field, but still over F2. So you need to get into the details of Reed-Muller codes to actually understand how the questions and answers look like, and hopefully after Amnon stock, we'll be able to at least say more about this test.
Okay, so let me say what I am after. Like, yeah, here you ask it as if you are like the players have some function in their mind, and you're applying the BLR test to this function to see if it is a linear function. Now, if you take,
I can force them to have a function, Guy.
You force them to have a linear function.
I know, I can force them to have a function. A function is answering numbers either 0 or 1 to me, right?
Yeah.
We play a game, so they have a function. They have the way, the strategy that they answer their game. So the only thing I do is checking that it is linear. Yes, exactly.
Yeah, so you're checking that this function is linear. Now, a linear function this is a linear function over a very large space.
Right.
A linear function over a very large space, if you rename the points in the space and also take a very small subset of the space, that linear function can be thought of as a low degree function, which is not linear.
Okay, why? I don't understand. On any subspace, it's linear.
The Hadamard code, if you're encoding a vector.
Yeah, I'm thinking that they have a linear functional, And every linear functional has a dual, right? The dual is just a vector, and actually checking that the function is linear is the same as encoding this vector using the Hadamard code.
Yeah, okay, fine. You have the Hadamard code encodes for every functional the value of the functional.
No, it's the other way. The functional can be defined using a single vector, which is much less information than the whole functional, right? The functional is the Hadamard encoding of some vector. What is a linear? What is a linear
We're
function?
not talking about
It's just the inner product.
Okay, the Hadamard. Okay, just hear me out and tell me if what I'm saying is true. It's maybe not the language that you're thinking about it, but if you have a vector and you want to encode it using the Hadamard code,
yeah,
one way to look at it is that in the Hadamard code you have an entry for every functional. So the vector is from the vector that you're encoding is from some vector space. For every functional on this vector space, you have an entry in the Hadamard code, and in this entry you put the value of this functional evaluated at this vector.
right.
So that's the Hadamard code.
Right.
For a low degree encoding.
So let me exactly say it the other way around. Okay.
No,
instead of
why?
encoding, because this is the way you should think about it here. Every point, a functional, a linear functional,
you
exactly
want the
taking
be,
every point
okay,
in your space and put it in your linear functional. This encodes the dual of the functional, right? This is exactly what you're saying it the other way around, but
yeah, it's
when
just,
you say
every vector you can call it a functional, and every functional you can call it a vector. It's fine, but because
here it's important because I think of it as inputting some V and W inside my function, and this is why I think it's more.
But okay, I just want to carry it one step further. So let me continue in my language. We are encoding a vector, and we have an entry for each functional. Now, when you have the same vector and you want a low degree encoding of this vector, you want to encode it as a polynomial of low degree. One thing that you can, one way that you can think of a low degree encoding is by thinking of the vector as representing the value of a low degree polynomial at several points, and then the encoding of the vector is the interpolation of those points to a low degree polynomial.
Okay, yeah, I'm with you.
Now, what is an interpolation? An interpolation of a set of values of a polynomial is obtained by, for each new point, the value is some functional of the interpolation points.
Yeah, but it's different for different points. This is the
for every point you have a different, so to interpolate a fixed
I'm with you.
You have for each new point some functional. So basically you have a subset of the Hadamard encoding, right? You have not all functional, but just these functionals that are useful for interpolation.
Okay.
Yes, I think that's true. I think Anand Natarajan explains it this way in the talk, which I just put the link to.
Yeah, actually, this talk also appears on my website as a favorite. So please, if you want to understand better what I just said throughout this hour, he probably explained it much, much, much better. So this is a very good talk. But Guy, okay, I'm not sure. Like if Dorit says that this is exactly how Anand explains it, that's good. But I usually think of it as the following thing.
I'll take the responsibility.
No, it's okay. My point is the following. A linear functional, you can encode it using a vector. Okay? The linear functional is exponentially larger than this vector. the information of this functional, like evaluating the functional on every point, is much larger than the vector you started with.
Yes.
But this is exactly, encoding the vector as a functional is exactly the Hadamard code, which means that it's locally testable. Now forget the functional, go back to the vector. Encode it using the Reed-Muller code instead of the Hadamard code.
Yes.
In this way, you use much less, I don't know, you enlarge the information in only polynomially and not exponentially. Yes. And now this still has a local, this is still locally testable. And
right. Yes.
So the point is, instead of taking all these XVs, define something like X, okay? So X point or X line, okay? We have these XVs and ZWs. Instead of them, define X point and X line. And again, this, you should think of the answer to X point as if I would ask you for the value of your polynomial at this specific point, and these polynomials are the X polynomials, you should answer this way. And yes, like the functional encoded the same vector, now this encodes the same vector. So somehow they are able to use this much more efficient encoding to still get a representation of this group. I don't know, this is the way I see this thing.
Yeah, so all I'm saying is that in some sense, this low degree encoding is in some sense a subset of the Hadamard encoding. And what I wanted to...
This is the way you think of it. Wait, but the answers are much larger.
Yeah, because the answers are larger because you're not actually asking about the encoding, you're asking about whole lines in this encoding.
But even when I ask for a point, I'm asking for a point that an answer with a much larger field.
Yeah, so
maybe you are right. Maybe there is a way of thinking. Okay, but there is like, you don't need anything more than the Hadamard code, right? It's the largest code you can, like anything larger than it, it's redundant. So in some sense, any code is a subset of the Hadamard code, right? Or maybe I'm missing something.
Is the long code?
No, maybe I'm thinking about the long code. No, maybe I'm confusing something. So
no, the Hadamard code is the largest linear code, and the long code is the largest code.
Largest linear code. Right. Sorry, the largest linear code. Yeah, but the Reed-Muller is.
Yeah.
Okay, I need to think about it.
Reed-Muller is linear, except that the
Reed-Muller is linear. Right. Because some of the low degree polynomials is a low degree polynomial. Yeah, right. So yeah, so it needs to be a subset of the Hadamard code, right?
Yeah. Okay, I guess we'll see.
Are we closing the business for today?
Yeah, we're over.
Yeah, I think people already left, so feel free to go, but I will not talk about answer reduction. I think we will only talk about it at the end of the semester, and I'll at least say what awaits us. So next week, Alon will talk. After that, we will have a 1 week break. After that, Amnon will talk, and hopefully, Guy, I need to speak with you and check the tarikhim with you, but hopefully you will talk after that, okay, about PCPs. So we plan to talk about PCPs in a few weeks.
In these days, planning a month in advance sounds like
more than
completely outrageous. Yeah.
Okay, great. So see you next week.
Ciao.
ביי. גיא, אולי תישאר רגע, נדבר בכל מקרה?
אז אפשר לדבר